Okay, hello everyone. I'm doing the presentation on MedKLIP, Medical Knowledge Enhanced Language Image Pre-training. The paper is by Xiaoyi Wu et al., and the presentation is by me, Sunita Bernay. So I first want to talk about the motivation behind this paper. Medical diagnosis requires more in-depth knowledge of the medical field, and that puts off a lot of people because obviously there's a lot of people who want to diagnose something that don't have full knowledge of medical terminology. Also, the major growth of generative AI models, there is a very unique opportunity to apply some of those new discoveries in generative AI to the medical field, which this paper wants to do. So we'll start off with the problem statement. So given a query by a user about a specific medical condition that appears in an X-ray, how do we train a model to, one, predict the probability that a given X-ray image shows a sign of the provided issue/disease? And if there is a probability that the issue or disease shows up, we want to know where it occurs in the given X-ray image. So for example, if I don't know, looking at something like tuberculosis and I provide the image here, I would expect if I had tuberculosis to get a heat map of the area where the tuberculosis seems to show up or where the AI model thinks it shows up. So this is the main goal of this model. So some of the challenges associated with this model and creating it is medical reports often contain language that is esoteric to the common person. So a lot of the verbiage requires a medical background. And this makes it very hard for the AI to diversify, if you will. It can't very well be tied to a one-to-one thing. And aligning text with images is especially difficult for medical imaging because there's multiple ways to describe a certain issue or disease. And also locality is dependent on the way or context it was written in the medical report. So now I want to talk about some novelties and contributions of this paper. The first contribution is report filtering. At the time the paper was being written, there was no well-defined pipeline of filtering reports. Basically, you took all or most of the text from a medical report and you used it and you put it through your pipeline. However, MedKLIP is smarter about this, and they use a filtering pipeline to make sure they only extract information that's useful for identifying the disease. Second is the transformer-based text alignment. While this isn't a new thing in the area of machine learning, it is new in the medical domain. And this is a novel paper because it's using transformers to basically map language-based models with images and to make predictions based on those pairings. Finally, we have application of known medical knowledge for embeddings. Unlike other models which have a process of text embedding, MedKLIP embeds text in from reports using external data. So they're not just using text that was given to them as input, they're instead aggregating other data that we already know in the medical field, which can really help the accuracy of the model. Next, I'll talk about the related work. So VLPs are a related work, and they're kind of like the alternative way of doing this. You either have two stream methods or single stream methods. The core flaw with these models is that it takes both medical images and medical records at face value. And it doesn't use any externally available medical data, so it can make it less robust. The second related work is medical named entity recognition models. These basically are used to extract entities from medical reports. In case you don't know what an entity is basically the thing you're looking for, the disease you're looking for in a medical report or whatever the doctor was looking for. So that's an entity. And MedKLIP expands on this by integrating medical named entity recognition models into their pipeline. And we'll see how that works later. Finally, for the last related work, we have medical knowledge enhanced models. And this describes any model which uses already known medical data within its implementation to enhance data it's trained on. So as I was describing earlier, it takes outside data. It doesn't just concentrate on data that it was given it as an input. It references outside medical knowledge to enhance its encoding for text. And we'll see how that also works in MedKLIP. So now I'll talk about the proposed approach. So here's an outline of the model and what we'll cover. So first we'll talk about the report filtering, which is this node here. And then we'll talk about visual encoding, which takes the visual aspect and encodes it, entity encoding, which relates to the text and extracting what we want from the text here. And then the fusion model, which combines both the visual aspect with the text aspect. So first I'll talk about report filtering. So report filtering works by simplifying the data in medical reports. The paper states there's a specific shape of these simplified descriptions, and they call them triplets. It's kind of an odd name, but really it's just a 3-element tuple or a vector with 3 entries in it. So the authors claim they use this because it actually speeds up the processing of textual information. And if you think about that, that makes sense because there's less text being put through the pipeline and it's more distilled. So this is an example of the 3-element tuple I was talking about. We'll expand on what each of these elements are. So the algorithm basically divides sentences divides the medical report into sentences. We call S sub J. S is the sentence, and then J is the index of the sentence. So the first sentence would be S sub 1, so on and so forth. This is processed and converted to a triplet via a variation of the rad graph model. So a rad graph model is basically an entity identification and extraction model that they use from another paper to extract entities and other things like position and existence. So this is our text filtered model, which is the rad graph model, which is already pre-trained. They don't train it in this paper. Then we have the issue in question, which we call the entity. So it might be, I have the flu, I have the cold, I have pneumonia. So this is what we're basically looking for in the medical report. Then we have the position of the issue inferred from the text. So in medical reports, I'll often look at the X-ray and have some information about where it's located. And finally, we have the exist. And basically, this is telling us whether we are telling, or the report is telling us that there is something like a disease there, or there's lack of something there. So not all medical reports are going to tell you there is something there. Some of them will say there's not something there. So we need a way to tell the model that there sometimes may not be something there. So we can add this exist parameter to tell the model that. Just as an example, we can say that the entity is tuberculosis. The position is the substring located in the right lung. And then the exist is images show its presence. These would all be substrings or excerpts that were taken directly from sentences in the medical report. So you might be wondering what N is. So N can be one of 2 things, depending on how it's parsed. So N can be the extracted substring from the sentence, like we saw in the previous slide, or sometimes the sentence doesn't contain information such as entity, position, or existence. So in those cases, we just set it to 0, and it just tells the model that there's nothing there. We didn't parse anything, and it can ignore it. Next, I want to move on to visual encoding, which deals with images. So we take X-ray images, which are 3 channels that have an arbitrary height and width, and we extract features into a set called V. And so the visual feature extractor is a ResNet 50. And the reason they're using a ResNet 50 as opposed to something maybe more powerful is because they wanted to stay faithful to the comparisons to other models, which also use a ResNet 50. But keep in mind that this visual backbone can be replaced with another more powerful one if you feel it does better. And then our X here is our image input from the test data. So we're placing it in this visual backbone model to extract the features into V. Next, we'll talk about entity encoding. So entity encoding is interesting because it almost expands the entities to provide more elaborate descriptions. So for example, in our report filtering, if we extracted an entity such as tuberculosis, we can use a model like Clinical BERT to encode these into a much larger and more elaborate description, which gives us a lot more detail and a lot more data to encode. Clinical BERT is a text encoder built specifically for the medical field, and its main goal is to take smaller, more esoteric terms from medicine and convert them to more descriptive terms. So that's basically what enables this to turn into this. This is, again, a pre-trained model, and it's used here. It's integrated here into the model in MedKLIP. So after we resolve descriptions for the entities, we then pass the description to a text encoder. As I said earlier, they use the Clinical BERT for the pre-trained text encoder. So here we have our E here for our entity, and then we have our textual encoder, and then we pass in our description. So in text encoder is a Clinical BERT plus MLP. For MLP is for linear projection, so we can project into a dimension that we want. And then the description is the resolved description from the entity we parsed from the report filtering stage. Similarly to entity descriptions, we also use the same text encoder to encode position data from the triplet. So that position data we extracted from the report filtering stage. We also perform the same encoding here. The only difference is we're putting position here and we're storing this into P. Now we can combine all of these results and get the following. So we started off with this from the report filtering stage, and now it's been transferred into this EPL. We know what E and P are, but L might not be familiar. L is basically exist, but it's been reduced to a binary 1 or 0, 1 for we're seeing if it exists, and 2 for we're showing it doesn't exist. So now we move on to the fusion model, which combines both the visual and textual aspect into a transformer. So the model takes the most popular entities first from the parsed triplets, and we store them in a set called Q. So for example, these are all the sentences within the report, and this is our EPL from the last slide. We take the most popular E's from this set. We're looking at entities right now. So we look at the E's here, which ones are the most occurring out of the whole report. And then we generate our Q. So we just put in the different E's that are the most popular into our Q set. And this gives us a set of the most popular entities stored. We do the similar thing with positions. So instead of looking at E now, we're going to look at P and say which one of these P's is the most, occurs the most, and we will put that into the P set, which tracks how popular each of these are. So now that these popular occurrences of positions and entities have been extracted, we can pass it into a transformer. So in a transformer model, we have Q, K, V, which Q is the query, K is the keys, and V is the values. In this paper, the query is the entities, and the keys and values are actually the image features. So we combine keys and values into one thing. So our prediction for S, P, and M is the fusion module, where we take the image V, which we extracted earlier from the visual encoding step, and we put in Q, which is our entities. So S here is the prediction indicating the presence of entities. So if you're looking for a disease, it's going to give you the probability it exists. And this is the prediction of the spatial positioning of the entity. So this is what predicts where in the image an issue or disease exists. Then finally, the M is the cross-attention maps outputted from the transformer. Finally, I want to talk about loss. So it uses the following formula, L sub LOC. And if you're familiar with this equation, this is a contrastive learning loss. So basically what we're trying to do here is we're trying to look at, if you notice, we're using P, predictive P, and then the ground truth P. We're trying to basically, if they're in the same class, minimize the amount of space between two different positions. If they're in the same class, and if they're not in the same class, we want to maximize the space between two positions. So this is a contrastive learning loss. This only applies to positions, but we also need to care about the actual predictions, like the probability that a disease exists. For that, we use cross entropy loss, and we integrate them both together. And we have alpha 1 loss of location and alpha 2 loss of cross entropy loss. Alpha 1 and alpha 2 are configurable hyperparameters that can control how much penalty you want to give to each of these different losses. So once again, this is the visual model. I just wanted to show this again after explaining how it works and where everything fits in. We can see with the text filter, we have our entity positioning exist, and we usually use a Boolean for that position, and then the entity opacity, I don't know if I'm pronouncing this right, phenothorax, and we pass it through the text encoder and we get the location embeddings. And obviously we have our visual here and our text encoder, we put it through the fusion model, and then we use contrastive loss to train it. And in addition, we have to use the report filter for that contrastive loss to train, or for it to learn what it lost for the text embeddings. Now I want to move on to experiments. So for the data, all of the data sets are paired medical reports with X-ray images. For pre-training the model, the authors use the MIMIC CXR version 2 dataset. And for training and testing the model, various data sets are used. These are all of them. You have chest X-ray 14 with the train split of 0.8 and a validation and test split of 0.1. Sim ACR phenothorax, which is a train split of 0.6 and a validation and test split of 0.2. I'm not going to repeat the numbers because they're all the same at this point. RSNA pneumonia, which is, and then we have COVID CXR2, and then edema severity. So some baselines, the authors use the following alternative models as a baseline for this model, which is Convert, Gloria, and BioVille. Convert and Gloria are actually retrained using publicly available data, the MIMIC CXR, as they both use proprietary data by default. So in order to make the test fair, they need to use publicly available data because they need to use it with their model. So they need to retrain these ones that have proprietary data in their research papers to use public data that we're going to use in the data set, or the testing the data. So I'll go over the evaluation metrics. AUC is the area under the receiver operator characteristic. And then we have F1/accuracy. It's a standard machine learning metric that combines both we basically take the recall and precision and combine them both into a single metric. And then standard accuracy is just the ground truth measured against the predictions and the difference. Pointing game is a metric that compares the predicted heat map against the ground truth heat map, and it decides if there's any meaningful overlap, and it's positive, otherwise it's negative. So this is actually a binary comparison for heat, or for like spatial masking and masking data. So it's not a scalar value, it's just binary. Then we have IOU, which is basically measuring the amount of overlap between heat maps. This is similar to the last metric, except we get a actual like percentage value or continuous value for how much overlap there is. Then we have precision and recall. These are both common ML metrics. For review, precision measures how much true positives we have, and then recall measures the percentage of how many positives were true. So here are the results. On the 3 data sets, RSNA, SIM, and chest X-ray 14, MedKLIP achieves significantly better scores for the AUC, F1, and ACC metrics. So you can see here that there's quite a big difference between the scoring between the highest and lowest. So it definitely beats a lot of models, and it's definitely showing to be a lot more verbose in these metrics here. In further tests, they do other data sets such as direct COVID-19 and COVID-19 description. And here, interestingly enough, in direct COVID-19, the scores are not that much better like they were in the last slide. They don't really provide a reason here, but it was kind of an interesting thing here. And also, we have the COVID-19 description, which they do actually do a lot better. There's a lot bigger difference in these data sets than the other one. So finally, I'll move to the conclusion. So some of the strengths of the paper is that this model is extremely innovative and it has a lot of foreseeable applications in the future. Due to its scoring, as we saw previously, it looks to be the most accurate in its domain for basically predicting diseases in images, which is really good because it makes it more robust. Also, the paper was very clearly written. There's almost no ambiguity, and the authors even provided explicit numbering for explicit parameters and everything for building the model from scratch, which is really cool. I haven't seen that a lot in a lot of research papers. Some of the weaknesses are the researchers state the ResNet 50 is used as a backbone because they wanted to make the comparison with other models fair. But it would have been better, in my opinion, to have some further discussion on the effects of different visual backbones. I think it was kind of a missed opportunity to show that the model can be way more diverse and way more robust if a different backbone was used. There's lack of empirical runtime performance data. If a model, it's one thing if a model performs really well in accuracy, but if it takes, 10 times longer to do, it's not very usable. So it would really be nice to have some empirical runtime performance comparisons because we would want to know how well we can scale this in the real world. Finally, I'll give this score, and my score is a 1. Even though there's a lack of metrics for certain places in this model, it's easy to forgive given that the implications of this model and improvements can be a very big foundation for a lot of other papers. The use of the transformer will allow this model to be reversed and be foundational to other future models. As seen in image generation and computer vision, in addition, the model is straightforward to understand. And as stated previously, this model can be potentially used by people who aren't professionally trained in the medical field to predict diagnosis, thus broadening its global impact on the field in a major way. So here's some future directions I thought of. As implied earlier, I would love to see a new variant of this model that uses a different visual backbone, which may improve performance. I was kind of thinking of using a visual transformer. Maybe something like that would make the performance of it a lot better. And also this paper mainly focused on X-rays as input. However, could we also use other different medical imaging formats? And is this model still applicable in those situations? Thank you. And